Hi everyone. Today I am going to discuss about current components of PN junction diode and diode current equation. Myself, B. Krishna, Assistant Professor, Department of ECE, University College of Engineering, Adhikavinan University. So this is the current components of PN junction diode block diagram here. So basically, as you know, the PN junction diode means there are two types of semiconductor materials are combined together to form PN junction diode. Those are nothing but, so this is the P-type material and this is the N-type material. As we discussed in previous classes, so here P-type impurities are doping for the particular silicon crystal. So this is the crystal material. First of all, the crystal material is taken from some crystalline silicon material. On that material, half of the side we are doping the P-type impurities, then it is formed. And another half of we can dope the pentavalent impurity atoms, then it is formed as N-type material, and those two are combined to each other. Okay, and then so this is the white space here, like it is a junction. So here nothing but it is the depletion region. So how it is formed? Due to the concentration of charge carriers from P side to N side and N side to P side, such as majority charge carriers. So due to these immobile ions, here the junction is formed. Immobile ions means here in N side the majority charge particles are electrons, such as negatively charged particles. In P side the majority charge particles are holes, such as positively charged ions. So here majority are holes, here minority are holes. So means the concentration gradient of holes are very more compared to this N side. And coming to the N side, here majority charge particles are electrons, and here the minority charge particles are electron. So here concentration gradient of the electrons are much more compared to this P-type. So due to that concentration gradient, the charge particles are moving from P side to N side and N side to P side. So then the positively charged ions are moving from P side to N side. So then they leave negative ions here. And similarly, the negatively charged ions are more here. They are moving towards the direction. Then the positive immobile ions are leave near the junction. Then the depletion region is formed here. So this is the basic concept of formation of this particular PN junction diode. As I told you in previous classes, so there are, as we discussed, such as open circuit PN junction and energy band theory for P-type and N-type materials, and energy band diagram for P-type and N-type material also, and also PN junction diode operation in two biasing conditions, such as nothing but forward bias condition and reverse bias conditions, and also discuss the VI characteristics of PN junction diode. Now here I am going to discuss about current component of PN junction diode. So here current component, what is meant by current components? Currents. So what are the currents are available in this particular PN junction diode? So such are nothing but components of PN junction diode. See here, basically let us see here. Here the majority charge carriers are holes. Here majority charge carriers are electrons. So the current is generated due to the majority charge carriers. That is one type of current component. And also there is a minority charge particles. Due to that, another current component is also generated. Nothing but that is another current, minority carrier current. So these are the current components. Let us first find here, observe this. When a PN junction diode is forward bias condition. Here let us see here. Here we are making the positively charged ions are more here and negatively charged ions are more here. Here it is a negative terminal. Here it is a positive side. For positive side, we are making the connection with the positive terminal. Here negative side, we are making the connection with the negative terminal. So then this diode is going into forward bias condition. Okay, let's. So here, when a PN junction is forward bias condition, a large forward current flows due to majority charge carriers. So then the depletion region is very small. Why the depletion is very small? Because of due to this forward bias condition. This is the when the positive terminal is connected to positive charge area, negative terminal is connected to negative charge area, then the diode is going in forward bias condition, or the diode is working in forward bias condition. Then only the majority charge particles are fastly move towards this junction, and here the minority charge carriers are fastly move toward the junction. Then the depletion region will be decreases. Means the majority charge carriers from p side and n side are moving towards the junction. So they are moving towards the junction fastly, and they hit to the junction, then automatically the junction width will be decreases. Coming to second point here, in forward bias, holes gets diffused into n side from p side, while electrons get diffused into p side from n side. Okay, and here, so on p side, current carried by electrons, which is diffusion current due to minority charge carriers, it is decreases exponentially. It is decreases exponentially with respect to the distance from the junction. It is denoted as INP. So this is the INP here. Okay, right. So let us see this diagram. Let us see this diagram. This one. So here, this is the p side area, and this means the n side area at junction x equal to 0. So here, as I told you, here majority charge particles are holes. Why? Because here, due to the majority charge current is more. So this is the current here. As the applied voltage increases, then the charge carriers are moving towards the junction. So here, majority charge carriers are electrons. Here, majority charge carriers are holes. They are moving towards the junction. Then they are decreasing the concentration gradient. So then, when they are entered at the junction, after that, the distance increases. The charge carrier current will be decreases exponentially like this. Okay, here the charge carriers concentration is more. So due to this forward bias condition, the current is having to generate more current than it is the current here initial stage. By increasing this voltage, the carriers are moving from p side to n side and n side to p side like that. So then the IPP means whole current on p side. Whole, this is the whole. P means whole on p side. So it is more. By increasing this forward bias condition, by increasing the external voltage, then the charge carriers are moved towards the junction. After entering or after passing through junction, the concentration, the speed of the charge carriers are decreases. Why? Because the holes here act as minority charge carriers. That minority charge carrier current will be less. So means when the holes are entering into the n side, the current is also decreases in this way, exponential form. In this exponential notation, it is decreases. As well as here, coming to here, whole current in n side is more. Why? Because here the majority charge carriers are holes. Due to that, current the generated is very much compared to the minority charge carriers in the p side. So when the charge carriers are moving towards the junction, after leaving this junction, the majority charge carrier here, electron, such as in this p side, or minority charge carriers. So in p side, the minority charge carrier current is very less. So it is decreases in this way. It is decreases exponentially in this way. So these are the basic current components of the particular p-n junction diode, such as here, like see here. If the distance is denoted by x, here INP x equal to current due to electrons in p side as a function of x. And similarly, IPN of x is nothing but whole current in n side. So this current is nothing but minority charge carrier current. So here, as the distance is increases, let us see here this point. So on p side, current carried by electrons, which is diffusion current, due to minority carriers, it is decreases exponentially like this. So here, see here, it is decreases exponentially, or it decreases exponentially because of because of with respect to the distance from the junction. With respect to the junction, here the distance will be increases like this. Why? Because by applying this voltage here, the charge carriers are moving away from the junction. These are the minority charge carriers. Those minority carriers are away from the moving away from the junction. Then the distance will be increases from the junction. Then automatically the current will be decreases. Okay, so this is the minority charge carrier current IN. IN means electron current on P side, that is conduction due to electrons in P side as a function of X. Similarly, hole current in N side, current due to holes in N side as a function of X. So this is the complete overview of this particular slide. Coming to the next one, at the junction, let us see here, at the junction, that is at X equal 0, electron crossing from N side to P side and constitutes a current nothing but INP. At the junction, nothing but at X equal to 0, electron crossing from N side to P side. That current constitutes a INP of 0 at junction. That is here. Here, that current is nothing but here INP of 0. Okay. Similarly, in the same way, in the same direction, the holes are crossing the junction from P side to N side. That constitutes current. That is nothing but IPN of 0. It is in this way. Here the holes are crossing from P side to N side. Then the IPN of 0 is like here. Here it is represented as IPN of 0. IP means holes current. N means to enter the N side. Okay, like come here. So hence the total current, total conventional current I at the junction is I equal to IPN of 0 and INP of 0 at junction. At junction means X equal to 0. X equal to at X equal to 0. The total current is at IPN of 0 plus INP of 0. Okay. Now INP of 0 decreases on N side as move from the junction N side. Okay, this INP of 0 as a function here, if the function X is varies, see in this diagram, here this is the function of X, as function X is varying along the distance in N side as well as the function X is varying in P side along with the distance. Then what happened? So what are the components here, such as measured charge carrier current from N side to P side and P side to N side, such are decreases. Then the X will be varying. Then only he says INP of X. N means electron current on P side. Here X is varying means the junction, the distance will be increases from the junction. Distance will be increases, then what happens? The current will be decreases exponentially. Okay. Similarly, INP of X decreases on P side as move from the junction. Here now INP of X is decreases on N side as move from the junction N side. Similarly, INP, like there is some mistake here. Here it is IPN of X. Here it is IPN of X decreases INP of X. Okay, IN electron current on P side, hole current on N side. Okay, right, good. IPN of X is decreases on P side. Sorry, there is some here. Now INP electron current on P side. Okay, here electron current on P side decreases and P side move. Okay, right, good. Similarly, the it's not right here. It's correct. No problem. Here INP of X is decreases from P side on P side as move from the junction, as move away from the junction. That's why here the minority charge carrier current will be decreases on P side. Why? Because as varying the function of x, as varying the function of x means that charge carrier some travel from the junction, then the current will be decreases. That current is only due to minority charge carrier current. Okay, but here let us see here, but the total current maintained at I is independent of x. On P side there is exist one more current due to minority carrier current, that is this one IPP of x. Okay, let's see here. So this IPP of x equal to current due to holes on P side. Similarly, in N side, one more current component exists due to major charge carrier current. It is denoted as INN of x. Okay, here, so this is the wrong word here. Majority charge carrier current. This is the majority charge carrier current, such as holes, that is IPP of x, that will be exist on P side due to hole concentration. Similarly, in N side, one more current component exists due to major charge carrier, that is nothing but denoted as INN of x. So this current due to electrons on N side. Let us see here. So here on P side, total current on P side is I equal to IPP. IPP means all current on P side of x plus INP of x. Similarly, on N side, I equal to INN of x plus IPN of x. So this is the total current on N side, and this one is the total current on P side. The current IPP decreases towards the junction. At the junction enters the N side, it becomes IPN. As I told you here, this point is rising here. Let us see here. The current IPP decreases towards the junction, towards the junction. At the junction enters the N side and becomes IPN. It is further decreases exponentially. Why? Because it is further decreases as the distance is increases, the IPN is decreases. This IPP is changes IPN when it is enter into the N side, then IPP is as converted as IPN. Nothing but minority charge carriers in N side. Here majority charge carriers on P side. Okay. Thus the current INN, this point, thus the current INN decreases toward the junction, like here current component of P side. Similarly, on N side, the INN decreases towards the junction. At the junction enter into P side, it becomes INP. Electron current on P side. Here electron current on N side. So this is the major charge carrier current, this is the major charge carrier current, and this is the minor charge carrier current. This one is the minor charge carrier current. Okay, next. That is overview about the current components of PN junction diode. Now go for the diode current equation. So this is the diode. Here I am going to discuss about diode current equation. So this is the diode here. Let us observe here. This is P-type material. This is N-type material. The positive terminal here we are saying it as anode, and here another terminal is there. That is nothing but cathode. It is negative terminal. One more switch is here. That is S, and this is the external potential difference. By due to concentration gradient, the depletion region is formed here. The depletion region having some potential barrier voltage. Nothing but it is VT. How the potential difference voltage is developed here due to electric field intensity across the junction, it is developed as V0. So let us discuss about this diode current equation. So here we are going to discuss about the relation between current and voltages of diode. As I told you in previous slide, there are some current components are discussed. Based on that, here also we can derive the current of particular PN junction diode. So here we're going to discuss about the relation between the current and the voltage of diode. Here V0 is the barrier potential voltage in the absence of any voltage. So here, next point. The switch S is available. If it is open, then the device is open circuited. And if it is closed, if it is connected, then the device is going to forward bias condition. Let us see here. So this is the positive terminal. We are making to make a connection at positive side, and here the negative terminal we are making the connection at negative side. Then this diode is going to act as generally forward bias condition, because there is a switch is available here. If the switch is closed, if the switch is going to close here, then the diode is going to work as forward bias condition. Suppose if the switch is act as open, then the diode will be going into open circuited, because of there is no external DC supplies is going to particular diode. Okay, so here, so this will be forward bias of diode when if the switch is closed. Now consider the total current of this diode. Here I equal to IP plus IN, whole current plus electron current. So where IP is the whole current and IN is the electron current. Now this is the whole current. Here IP is directly proportional to delta PN. Delta PN means change in density of holes in N side. Similarly, where delta Pn is changing hole density in N region. Similarly, electron current equal to In. Here I is directly proportional to Np, nothing but electron density in the P side. Okay, where delta Np is the electron density in P side. Okay, so here the total current is I equal to IP plus IN, where IP is whole current, IN is the electron current. Now this is the whole current. So here IP is directly proportional to delta PN, where delta PN is the whole density in the N region. Whole density means change in density of the holes. So here the density is more, here the density is less. Why? Because the concentration of holes it is more. Here the minority charge carriers are holes. Here the majority charge carriers are holes. They are moving towards this junction. The concentration is less here. So change in density, high density to low density, like that. So here IP is directly proportional to delta PN. Similarly, IN is the electron current. Here again the I is directly proportional to delta Np, where delta Np is the electron density in P side. Now we are going to consider here two cases. One case is switch is open, then what happened? If the switch is closed, what happened? If the switch is open here without applying any external potential, the diode is act as an open circuited condition. Here the majority charge carriers are holes. They are moving towards the junction into N side, because there are carrier concentration gradient. Suppose here the electrons are more and holes are less. Here the electrons are less. Here the electrons are majority. Here the electrons are minority. Then the electrons majority charge particles are moving towards the P junction. So then the immobile ions are formed here the junction. So near the junction, then it is formed as a P depletion region, as I told you in previous classes. Okay, so here there is a minority charge carrier movement is occur through this particular electric field intensity. Why? Because this electric field intensity develop the potential difference. So this is the potential difference voltage V naught. Due to this potential difference voltage, there is a movement of charge carriers. Such charge carriers are nothing but minority charge carriers. Due to that minority charge carriers, there is a current, that is reverse charge current or minority charge carrier current. Okay, so now if the switch is closed here, it is second point. If the switch is closed here, so then suppose it is closed, so then the diode will be going to in working as forward bias current. So then the current is generated, that current is due to the majority charge carrier current. Next, so when I go to the case 1, the switch is open, so it is called as open circuited PN junction diode. Now consider the whole current density in P region. Here PP means holes in P side, hole density in P region, and then nothing but electron density in N region. So we can write Boltzmann relation. So here PP equal to Pn into e power Vp by Vt. Here Vb nothing but, there in diagram I given as, here it is V naught, here V naught is nothing but Vb. VB nothing but barrier potential voltage. Barrier potential voltage. Here is given that here PP is hole density in P region and PN is hole density in N region. Similarly, VB is the barrier potential voltage across the depletion region and VT is the whole volt equivalent of temperature. But here that value is VT equal to T by 1100. It can be represented in Kelvin at room temperature T equal to 27 degrees. But in Kelvin, the total here the value can be represented as VT equal to 26 millivolts. Where you can require this value, you can mention that value with VT equal to 26 millivolts. Okay. Let us see here. PP. PP means holes concentration in pin side. That whole concentration in pin side, total hole concentration, nothing but the change in density. As I told you in the previous slide, the change in density of holes, that is decreases exponentially as the distance increases from the junction. So Pn equal to exponential notation is e power VB by VT. Okay. So here, let us see here. Now the switch is open, then VB equal to V0 from the equation 1. So this is the equation 1 here. From equation 1, now the switch is open, VB equal to V0. VB equal to V0. So means there is no any external DC voltages applies. So VB barrier potential voltage equal to V0. Therefore, equation 1 becomes PP equal to Pn into e power. Instead of VB, we can write here V0 by VT. That is equation number 2. Next, suppose in case 2, when the switch is closed, then the PN junction diode becomes forward bias condition. Okay, as I told you in previous slide, let us see here. If the switch is closed, here, then what happens? So this potential voltage will be applied to this particular diode. The positive terminal connected to here, positive area, the negative terminal connected to the negative area. Then here the negatively charged particles are more. By applying negative potential here, they are repulsing to each other. So there is no chance the charged particles are moving towards the junction. So here positive charge area, here the switch is closed, the positive terminal connected to positive area. So obviously they are moving toward the junction. Why? Because these are the measured charge particles such as having positive charge. At positive charge, we are applying positive terminal, then they are repulsing to each other, they are moving towards the junction. Okay, because of this condition. Okay, now when the switch is closed, then the PN junction diode becomes forward bias. In this case, barrier voltage V naught is decreases because of the applied voltage V is opposite direction of barrier voltage. So what is the meaning of this condition? This point, let us see. Let us go through the diagram. Okay, so this is the barrier voltage. So here we are applying the voltage. Here the electric field is going to in this way. The force is the electric field direction is from ends positive charge to negative. The direction is going in this way. Here we are applying this voltage. This direction is going like this way. It is opposite to this electric field intensity. Then automatically they are opposite to each other. Then automatically this depletion region will be decreases. Means if the depletion region decreases, then the potential voltage V0 is also decreases. This is another concept. But behind that, there are measured charge carriers are moving towards the junction, and the measured charge carrier moving towards the junction, automatically the depletion is also decreases. This is another concept. Okay. So that is the meaning of this point. First point. Now, second point. Now the barrier voltage becomes, so when the diode is forward bias condition, in this case, barrier voltage V0 is decreases because of the applied voltage V is opposite direction of the barrier voltage. Now the barrier voltage becomes, it is the V0 minus V is the resultant voltage is available at the junction. So the diode is in forward bias, the difference voltage at the junction VB equal to V0 minus V. This is the barrier voltage. Now calculate the delta Pin, means change in density of holes with the forward bias. Then the whole current density in N region increases from delta Pn to సారీ Pn to delta Pn. చూడండి ఇక్కడ ఏమవుతుంది, now the barrier voltage becomes V0 minus V, means when the diode is in forward bias condition, diode forward bias condition లో ఉంటే అక్కడ బ్యారియర్ పొటెన్షియల్ వోల్టేజ్ కొంచెం చేంజ్ అది అక్కడ అవుతుంది. ఆ చేంజింగ్ వోల్టేజ్ ఏముంటుంది ఇక్కడ మనం V0 minus V. V0 nothing but barrier voltage and V nothing but applied voltage. That difference voltage here he says it as a barrier voltage. So then calculate the change in density of holes in N side when the forward bias. Then the whole current density in N region increases from Pn to delta Pn. Now we are going to see delta Pn. Consider the equation 1. Okay, this is the equation 1. So instead of P here, we can replace with Pn plus delta Pn. This is the total change in hole density. Okay, replace this value. Instead of Pn, we can replace with the Pn plus delta Pn into e power. Instead of Vb, this is the Vb, V0 minus V. Again, we can replace with the Vb, V0 minus V by Vt. Clear? Next, by simplification here, e power V0 by Vt into e power minus V by Vt. Okay. Now from equation 2, here in previous slide, I given equation 2. So this is the equation 2. From equation 2, we can use Pp equal to Pn into e power V0 by Vt. So here, this is the Pp value here. You can substitute or equate in those two values. Replace the above value instead of Pp. Okay. Pp ప్లేస్ లో దీన్ని రీప్లేస్ చేయండి అన్నాడు. అంటే యాక్చువల్గా చెప్పండి ఈ పాయింట్ ని ఈక్వల్ చేసుకున్నా పర్లేదు, లేదా ఈ Pp ప్లేస్ లో ఈ వాల్యూని సబ్స్టిట్యూట్ చేసినా నో ప్రాబ్లం. నెక్స్ట్ స్లైడ్. సో హియర్ Pn equal to e power V0 by Vt, that equal to Pn plus delta Pn into e power V0 by Vt into e power minus V0 by Vt. So this V0 e power V0 by Vt and this e power V0 by Vt is cancelled each other. Finally, we are getting P0 equal to delta Pn plus Pn into e power minus V by Vt. So we can write the above equation. So this exponential notation comes this side, then the negative polarity is going like this. Why? Because so this value will be going left side. It is act as a denominator. If it is act as a numerator, then this minus is going to plus. దీన్ని ఇక్కడ మనం లెఫ్ట్ సైడ్ పంపించాం అనుకోండి, డినామినేటర్ వెళ్తుంది. యాక్చువల్ దీన్ని మనీ న్యూమరేటర్ తీసుకొస్తే ఆ మైనస్ కాస్త ప్లస్ అయిపోతుంది. ఓకే, ఫైనల్లీ Pn into e power V0 V by Vt into Pn plus delta Pn. So finally, our aim is to calculate here delta Pn. Delta Pn equal to ఈ Pn ని కాస్త కూడా ఇటువైపు పంపించేస్తే Pn into e power V by Vt minus Pn. So delta Pn equal to common term here it is a Pn, here it is Pn here. So common term you have take out this. So Pn equal to Pn into e power V by Vt minus 1. So this is the equation number 3. Again, taking the equation number 2, Pp equal to Pn into e power V0 by Vt. Pp equal to Pn into e power V0 by Vt. So this value e power V0 by Vt is transferred to the left side. Then it is going to Pp into e power minus V0 by Vt. ఇది ఎలా వచ్చేస్తుందంటే ఈ వాల్యూ లెఫ్ట్ సైడ్ పంపిస్తే డినామినేటర్ వెళ్ళిపోతుంది. ఆ డినామినేటర్ కాస్త న్యూమరేటర్ రాస్తే ప్లస్ కాస్త మైనస్ చేంజ్ అవుతుంది. దిస్ ఇస్ ద వాల్యూ Pn. So put the value of Pn in equation number 3. So then the equation 3 becomes like this. Okay. So here this is the Pn value. Here we are getting the Pn value. You can substitute this Pn value, this one, in equation number 3. So then the equation 3 becomes like this. Delta Pn equal to Pp into, so this Pp into e power V0 by Vt of e power V by Vt minus 1. So this is the equation number 4. Next. But in firstly, I can say there we have seen that the whole current density proportional to delta Pn. Okay, so here Ip directly proportional to delta Pn. That is Ip directly proportional to Pn. But I know the value Pn value is here equation number 4. This is the Pn value. delta Pn value, you can substitute that value in equation here. So IP is directly proportional to, actually here the delta is mentioned, but I did not mention here. IP directly proportional to Pn. So like this, IP equal to Pp into e power minus V naught by Vt into e power V by Vt minus 1. So the proportionality constant, for proportionality constant, IP equal to ISP, saturation current on P side, into e power V by Vt minus 1, where ISP is the proportionality constant. Okay. Similarly, this is the current for hole. Similarly, the current for electron, therefore the total current. Okay. Similarly, electron current, so this is the electron current. In equal to ISN into e power V by Vt minus 1. But we know that the total current is I equal to IP plus IN. So this is the hole current and this is the electron current. So obviously we are getting I equal to IP plus I naught. Substitute this value and this value, we are getting total current I equal to ISP into e power V by Vt minus 1 plus ISN into e power V by Vt minus 1. So here the common term is e power V by Vt minus 1, and here e power V by Vt minus 1. Take common to this point. So here I equal to ISP plus ISN into e power V by Vt minus 1. And here, so this ISP plus IN nothing but reverse saturation current or leakage current. So this I naught is nothing but reverse saturation current or leakage current. So finally we are getting I equal to I naught into e power V by Vt minus 1. Generally, this is the current equation. But here the current I naught is totally dependent on the temperature. That is I naught equal to ISP plus IN. Therefore, I equal to I naught into e power V by Vt minus 1, where I is the diode current and V is the external voltage. I naught is the reverse saturation current. So this equation we can write another form, another way. We can write the above equation for various material or other form of the above equation here. Various material means there are so many materials, silicon material, germanium material, and some other materials are available. Based on that material, the current equation, the diode current equation maybe changes, or it can be formed in another form. So like this form, I equal to I naught into e power V by eta Vt minus 1, where eta is nothing but ideality factor or ideology factor for various material. So here various material means these are we are going to discuss about germanium and silicon material. For germanium it is 1 and for silicon it is 2. So this is the final diode current equation of particular PN junction diode.